Yeah, so we will wait for 2 minutes more and then I will start. So, hello everyone. Today I will be doing two hands-on uh, and other are some videos. So, I will introduce myself. I am Anjali Negi. I'm currently a PhD student in IIT Kanpur. So, I think we should start. Yeah, so I am audible, right?
Yes, ma'am.
Okay, so let's start now. Yes. So this is GATE 2013 question, chemistry, question number 13. So this particular question state that the catalyst and the co-catalyst used in the Wakeup process respectively are. So
Ma'am, slide is not visible.
um, is this the same case for Gunasli too? Because I can see my slides in my other computer. Okay. So I am sharing my screen. So can you see that?
No, ma'am.
Okay. Do stop sharing. Now,
Ma'am, is there any question on slide?
yeah, I am presenting. It's GATE 2013 question.
Yes, ma'am, but I'm not able to see it. It's coming like screen broadcast.
Oh, okay. So I think there is a lag. So because if you are seeing the sync broadcast, so that was just some seconds ago. So I think there is a lag between us.
So should I join again?
I don't know. Your internet, your voice is very clear. So I think you should not go back. You can join again also. I will wait.
Okay.
Yeah. Yeah, for Gunasli it is visible. Okay.
now visible, ma'am.
Okay. So whenever if my audio is not clear or screen is not visible to you, you both can answer. Okay. Stop me in between. Yeah. So this particular question was from GATE 2013 chemistry question number 13. This question states that the catalyst and the co-catalyst used in the Wakeup process respectively are. So we are given with four options, and yes, in I think if you guys have just gone through a Wakeup process or anything in while you were studying, so you might, if you have an idea, then you can just get confused between, because all the four options contain copper and all the four options contain palladium, correct? But the correct option will be, we will find out. So I'll just go back. Yes. So basically Wakeup process is a oxidation process, and it is used for the oxidation of terminal alkenes. Okay. uh, al- yeah, alkenes. So we will just write it down that the process of oxidation of terminal alkenes to so the oxidation of alkene will make them convert into either aldehyde or ketones. Okay. Aldehyde and ketones. Now by using palladium and copper compounds as catalyst. Still we don't know the exact one, so in the next I will tell. So this is what is a Wakeup process is. This is what we call the Wakeup process. Okay. Now this palladium and the copper compound which are used as catalyst are actually palladium with oxidation 2. Okay. Chloride. I will just make it short note for you. So this is PD. Wait a minute, it's not that clear. Wait a minute. So yeah, it's PdCl2 basically, but so this is insoluble, and the process is using solvent water. So basically we have chloride ion in our solution, and so it will be giving me PdCl 4 S. I think what was the oxidation state there in our question itself? You can just check here. 2 negative, yeah. I think the screen sharing is off, right? Can you see my screen?
No, ma'am.
Okay. Yes. So this is the correct option, okay, in the case of palladium chloride, because this is one the soluble in water. And the number two is the copper 2 chloride. So these two are used in this process along with the oxygen and water. Now for example, so in the problem itself they have not given any example or not have asked any mechanism, but simply we can just have one example and look into the catalyst they have used, which we already did. So for example, we can take ethene, simple alkene, okay, and copper Cl2. So always see that this PdCl2, if you have just not simply noted that this PdCl2 is actually insoluble in water, and the actual catalyst is the PdCl4 2 negative. When the Cl negative just add up to it, and it makes, and the complex that is there is the PdCl4 2 negative, which is participating in the further mechanism. So that is the main point here to note, because that one is the soluble in water as a reaction is in water itself. So this will do the oxidation of alkene, and we will get this is as an aldehyde. Okay, so going back, yeah, so this was the Wakeup process. Now getting back to our problem. Yes, so as you have just seen now, so the correct option must be the option number D. So also there is a, okay, in option number B and D I can see that the respectively, they have used this word respectively. So the first catalyst is the, in the mechanism which is used, is the PdCl4 2 negative, and then later CuCl2. So the respectively word is very important here, and you have to check that B and D are all same option with same catalysts, but only the order are different. So look into that also. Yes, so the correct option is D. So let's move into another problem. So any doubt here? Okay.
No, ma'am.
Okay, so our next problem is the one. So this came in GATE 2013. This is question number 17, and this question states that the maximum number of stereoisomers possible for the compound given below is. So as I have not recorded this in the video, so I am having a little advantage here to ask you directly whether you can answer me correctly or not. So any of you can just type in your chat box that the maximum number of.
Ma'am, slide is paused.
So can you see the question?
I'm seeing question number 13 only. Previous one.
Okay. So there is a internet lag between both of us. So I think others can see, right?
Okay, I will join again.
Yeah, so others, Amruta and Gunasli, you both can answer on your paper, or you can just write down the answer if you already know on the chat box, in the chat box, and I will solve it then.
Hello.
Yeah.
Good evening, ma'am.
Yeah, good evening.
Ma'am, I would like to clarify that I'm not a student. I
Okay.
am from NPTEL. I'm here to monitor this session.
Okay, yeah, okay. Yeah, sorry.
No, no, not an issue.
Okay. Okay, so Gunasli or Shika, you can see the problem, right?
Yes, ma'am.
Okay, good. So the maximum number of stereoisomers possible, don't worry if you don't know the basic or any, it's not a problem. We will just quickly go through it and we will find out the correct answer for this particular compound or molecule. But if you already have some basics and you already have solved this kind of problem, then you can just type in the chat box. Okay, I am getting some answers now, so I will start solving it. Okay, then I will discuss the answer later. So yes, let's go back and so I think you can just see my whiteboard. So I will start. So yes, so talking about stereoisomers, first we should know some basic keywords or terms. So the first term that we encounter is the chiral word. So basically, this chiral word is uh, from Greek. So it's a Greek word, and it just simply means that it is the meaning of it is not super impossible. Okay. Means not super impossible. Yeah. Super impossible to what? Super impossible to its mirror image. Okay. So the basic example that we read in a textbook while we are getting introduced to this concept is our hand. So our hand are mirror images of each other and they are non-superimpossible. Hence we see that this is the example of a chiral or chirality. Okay. So when I talk about simply chiral molecule, or when I talk about chiral atom or atoms, okay. So what we see here that when I say chiral molecule, it means that it is not superimpossible on the mirror image of its molecule. On mirror image of its molecule. When I am talking about the chiral atom or chiral atoms, then I am saying that it is, so usually this stereoisomers and this chirality concept is usually we apply on the organic molecule. They have the backbone element as carbon. So usually there are usually are carbon atoms, correct, or atom bonded to four different groups. Yes. So this is number one word or keyword that we should get introduced to ourselves. And the second one is the stereoisomers. Okay. So basically, what are stereoisomers? So when I'm saying, so there are various kind of isomers. So isomers meaning they have iso means same, and whether they have the same chemical formula but different structure, or whether they have same chemical formula, but yeah, so isomer can be variety of type, but when I am saying that this word stereo isomers, so that means that the isomers that only differ in the three dimensional arrangement of atoms. Yes, so we will I will give you some example also, and in the end we will solve the problem that we have. So yeah, basically you can just take one simple example of your tetrahedral CH4 kind of molecule, where you can to make it stereoisomer, you can just simply change all the groups and make your this carbon as chiral atom. So let's say it have group A, B, C and D. Now this is very lame representation of my tetrahedral molecule, but instead of this, what I can do, I can just give it a 3D representation where my A and B are on the same plane, and my D and C are so D is say above the plane and C is below the plane. Okay, so that's how this the 3D of this molecule, 3D representation of this particular uh, chiral molecule, we can say, we can demonstrate in 3D space. Now this particular molecule having a chiral center is actually, it does have a stereoisomers, because it does have 4 different group, and one the carbon is chiral atom, and hence I think you guys know that it contains stereoisomers which are called R and S respectively, to the weightage of the group and the how we differentiate between them. Okay, now the other two keywords that we should know is, number one is the enantiomers. So first one is enantiomer. So enantiomer is stereoisomers that are non-super impossible mirror images. Okay, and the second one is the diastereomers. So this diastereomer is the stereoisomers that are non but okay, yeah, so that are non super impossible. The other thing is they are non mirror. So they are non mirror images, and so basically there will be some opposite configuration at some chiral center. So but in the case of enantiomers, they have opposite configuration at all chiral center. Yeah, so just to get it into your head, I think give you just one simple example. So say we have uh, wait a minute. Yeah, this is some bromine, chlorine. Okay, just don't bother about how the all bulky group are above the plane. Just for our understanding we are doing this. Yes, so this is say 1 2 3 and this one is the fourth one. Now if I ask you which one of them are pairs of enantiomers and which one of them are the pairs of distereomers, so if you look into the first and the second one, so we know that okay, so this is a chiral center, this is a chiral center, so they do have stereoisomers. Okay, so the first one and the second one, if I try to make them pair, so the first one and the second one are, yeah, so if I just, okay, just imagine when you are looking into this, just imagine that you place a mirror here and this mirror will reflect the molecule such that this bromine, which is right now above the plane, it will be below, correct? Yeah, so the mirror image of this one will be molecule 2, correct? So the mirror image is so 1 and 2 are mirror images of each other, and if I and they both, if I just put this molecule over the second one, so they both will be non superimposible. That's why they both are enantiomers. Okay, now number 2 and number 3. So when I look into number 2 and number 3, they are, if I just place one mirror here, just let's see, placing one mirror here, this bromine which is above or below, it will definitely reflect, but this chlorine, if it is below, it should must have gone above, correct? So they are not mirror images, correct? And since they are not mirror images, let's just try to superimpose them. So while trying, these two can get overlap, but these two cannot. So they are definitely non mirror images and they are non superimposable. That is why they are distereomers. These 2 and 3. And for third and fourth, I will just tell you guys that those two are enantiomers, and you can just do it again by reflecting the third one or by reflecting the fourth one, and you will find out that both are again mirror images, and yeah, they are superimpossible too, non superimpossible, sorry. So that's it, and there is again one note about meso compounds. So I will just draw one example here quickly, that so this is one group bromine, say there is one hydrogen there, bromine, hydrogen. Now if I say that okay, so this carbon is a chiral, this carbon again is a chiral, having 4 different groups, 4 different groups. So I have 2 chiral carbons in my molecule, but still they are not optically active, because the reason is the mirror image, whatever it will show or have, they both are superimpossible and are actually the same molecule. The actual reason behind is because of the presence of the plane of symmetry. Okay, so the because of the plane of symmetry, if you try to draw a mirror image of this molecule, so you will find out this both are same and super impossible on its mirror image, because at one glance if you see, but what happen is that at one glance if you see and then if you just simply rotate it and then superimpose, it will get superimposed because they have plane of symmetry. Okay, so I think it is clear, and let's get back to a problem. So this particular molecule that we have, okay, so there is another concept also which is very important before we solve the problem, is the stereochemistry of biphenyls. Okay, so biphenyls, when I am talking about them, so basically any biphenyl, if I just draw it here, so there is a sigma bond here which is used or which is here, and these two planar rings are freely rotating when there are no restriction present, and when they are freely rotating, then what happen, they are optically not active, or they don't have any stereoisomers, correct? But in case when they have some substitution or some restriction, so that the ring are perpendicular to each other or are restricted to rotate, then what happen, then for example, say you have, okay, so this particular case of biphenyl will show stereoisomers and will be optically active. So the point that I should note down is that there should be substitution on the ortho positions, whether it is a substitution in the ortho position or in the case, just I will just or in case some bridging ligand is present, something which is restricting the rotation of the two biphenyls, of the two phenyls. Okay, so that you can see. And the other second option is that on the same ring the ortho positions that are substituted must be different. Okay, so the substitution, and this is again because of the symmetry element, so we don't want, even if the chiral carbon or chiral atom is present there, we still don't want the plane or symmetry or improper axis of symmetry present in a molecule, if because in that particular case what happen is that it again reflects some meso kind of thing, and then it will get superimposed and it get optically inactive because of that, because of the symmetry present. But so because of that we don't want, so hence we I am writing down the point that the substitution on the ortho positions of same ring I am talking about must be different. Okay, yes, so this is there. And finally In the case of large substituents in that ortho position, so they will what these substitution do, they will interfere mechanically to behave as the obstacles and restrict the free rotation that was present initially. Thus these two benzene ring will become perpendicular to each other, okay, and hence the molecule overall become chiral, and the mirror image of this particular molecule now will not be superimposable, thus it will show a optical activity. Okay, so keeping this in mind, I think now we are good to solve our problem. Yes, so now this is one. I'm just trying to make it as a perpendicular portion. Yeah, so this is NO2. Okay, so you can see that this particular biphenyl, so this particular biphenyl group is a chiral molecule, or simply we can say it have stereoisomers because of the stereochemistry of biphenyl, as we have just seen. So we have stereoisomers from here, so they will have a total of 2, correct, and the other group that is actually present here, that is the bulky group, we just see that there is one chiral carbon present, which is this carbon, having one methyl here and other bulky group here, other group here, and this group is again different, and we have one hydrogen there. Okay, so overall this is a chiral carbon there. So another, because of this another chiral carbon, we will have other 2 stereoisomers, correct, and overall we will have total number of 4 as the stereoisomers present in this compound. So any doubt? So I think we can proceed forward. It's okay, right? Yeah. So we will jump to our next problem now. We still have time left. So let's just see. I think
Hello everyone. In this video I will be solving GATE 2016 chemistry question number 3. It states that among the following the most stable isotope to radioactive decay is. So we are given with 4 different options of lead where the atomic mass is varying. So we need to find out the most stable isotope among them. So before I go through the question, let's go through some basic. Here, the theory of radioactivity, it states that the nucleus whose N upon P ratio lies outside the belt are unstable, and therefore they undergo spontaneous radioactive disintegration. The nuclei with N/P ratio lying above or below the belt are unstable, so they undergo radioactive disintegration, giving out alpha or beta particle in such a manner as they will yield some stability or stable nuclei. So we can consider case number 1 where the N/P ratio, so the N/P ratio lie above the region of stability. This means that the nucleus contain too many neutrons. If it is above the if it is above the stability region, okay, so it will emit a beta particle, or we can say an electron, in the way that a neutron changes into a proton and the N/P ratio get lowered and come closer to the region of the stability. Okay, so this is the plot where number of neutron is denoted as capital N, number of proton as capital P, and the belt here is the belt containing stable nuclei, and the elements that is above or below are show radioactivity here. Okay. For example, this is the disintegration of isotope of carbon. This is just an example of the case 1 where 14C6 carbon is disintegrated as it and shows a beta emission, and it get converted into nitrogen with mass number 14, so 14 and 7. So the N/P ratio falls from 8/6 to 7/7, and it gets closer to the stability belt where the ratio get convert from 1.33 to 1. And the case number 2 you can consider where my N/P ratio lie below the belt, the stability belt, and evidently the nucleus contains excess of proton here, so it will disintegrate in such a way that the new nucleus has a high value of N/P, and therefore that it can come closer to the belt. This happens when by the emission of an alpha particle, that is a helium nucleus. So as a result that the new nucleus has lower charge and lower mass. So the unstable okay. So the unstable nuclei continue to emit alpha or beta particle until a stable arrangement is reached. Now, the tip here is that the N/P of N/P is equal to 1 is for the element number up to 20, and the N/P between 1 to 1.6 will be stated as the stable nuclei or nucleus. So we can say for that the N/P ratio lying between 1.6 and greater than 1.6 and less than 1 are stated as unstable. So for the given question, we are given with the 4 different isotopes, and I have written here the ratio corresponding to them. So the N/P ratio is for 206 lead 82 will be 124/82, that will be 1.51. And similarly, if you calculate an N/P ratio for all of them, you will get to know that the most closer to to 1. So what we need to check that the N/P ratio of given isotope should be more closer to or in between 1 to 1.6. They are actually in between 1 to 1.6, but the more closer to 1 will be the most stable one. So here you can see that the more closer to 1 isotope is the first one. Okay. So among the following, the most stable isotope to radioactive decay will be option number A. And I will refer you to go through the book Principle of Physical Chemistry by Puri Sharma Pathania, edition 2001. And the NPTEL reference is the lecture number 24, Radioactivity Alpha Decay, by Professor H.C. Verma, Department of Physics, IIT Kanpur. I have attached the link. Thank you.
So there are two more small problems that we can just simply play. We still have time. Okay. Yeah.
I will be solving GATE 2015 chemistry question number 26. This question stated, which one of the following statement is correct? We are given with 4 different options. So before moving to the option, let's discuss some basic. Now, the defects in solid are any irregularity in the pattern of crystal arrangements in solid, and this is called imperfection in solid or defects in solid. The crystal defect occur as point, along line, or in the form of a surface, and they have been classified as point defect and line defects. So we are focusing on point defect. So the point defect are the imperfection in the crystal that is due to the dislocation of a particle from one position to another position in the lattice. So this is for our understanding. So the types of point defect can be classified into stoichiometric defect, non-stoichiometric, and one impurity defect. So our main focus is on stoichiometric defect. So this defect is also called intrinsic defect or a thermodynamic defect because in stoichiometric defect, the proportion of the elements in the solid is not disturbed. So this defect arises when there is some vacancy in the crystal lattice or when some constituent particle move from their original site and occupy the interstitial sites. So the stoichiometric defect have been observed both, as you can see, in non-ionic solid and in ionic solid. Okay. So again, this stoichiometric defect in ionic solid, it is classified in two different defects, which is one Schottky, other one is Frankel defect. So to simply understand this, so in Schottky defect, it is the defect in the crystal is observed when, so you can see this is a representation of lattice. Okay, so this is a two-dimensional lattice where my cation are present in orange dots and my anions in negative blue. Okay, so this is the arrangement of arrangement in two-dimensional lattice of a ionic solid. So if I go through this demonstration, so to understand Schottky defect, this defect is also known as the point defect. And why is so? Because we observe when an equal number of cation and anion means both are missing from the lattice point. Okay, so the presence of the Schottky defect does not change the stoichiometry of the crystal. This has to be noted because at the same time the ratio of cation and anion is being neutral, so it is not affecting the stoichiometric of the crystal, but what it will affect the density of the overall crystal. Okay, so the presence of this defect lowers the density of the solid. So if this is my crystal, so after the defect, say this and this, one cation and one anion is missing from the lattice point. Okay? Okay, so overall, the density of the lattice will decrease. Okay, now to understand the Frankel defect. So Frankel is again simply in any crystal when ion leaves its regular site. Okay, when ion leaves its regular site and occupy an interstitial site here, it is now the ion is not leaving the whole crystal, but it is occupying the interstitial site. So this defect is termed as the Frankel defect. The only difference between Frankel and Schottky is that the density of the density in the Frankel defect, it remains constant, as my anion or my ion are actually not leaving the whole crystal, but the small size say cation will move to the interstitial site, okay, or space. So this defect will look like, say, this cation has moved and moved say anywhere in between here, okay, or here, okay. So this is the Frankel defect. So simply you can see the example for Schottky defect are NaCl or KCl. Frankel defect, it is AgCl or AgBr. Again, the point to be noted here that in Frankel defect, the size of the cation should be much smaller than anion. Usually it is smaller, but if it is smaller than the anion, then we can say that that the Frankel defect may be observed, because it will be easy for the cation to move towards the interstitial space or void. Okay. So this defect lowers the density of the solid, as I have discussed. Due to this defect, the atoms or ions can move within the crystal lattice. Correct? Due to this defect, the atoms or ion can move within the crystal lattice. Again, it does not affect the density of the solid. So these are the two differences. Now coming back to our question, which was asked that one of the following statement is incorrect. So option number A, the Frankel defect is a cation vacancy, which is correct, because cation is vacated from its lattice point and a cation interstitial. Correct. Frankel defect is an anion vacancy. It's totally not correct, because anion has a larger size, and we have discussed that in Frankel only cation of smaller size in comparison to anion move towards the interstitial site, and a cation interstitial, it is wrong. Okay. The density of a solid remains unchanged in case of Frankel defect. This is correct. Density of solid decreases in a case of Schottky defect. This is also correct. So the incorrect option is B. Okay. I will highly recommend you to go through NPTEL reference Lattice Imperfections and Crystal by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. The link is given below. Thank you.
Yeah, so any doubt if you have, so you can just type or ask.
No, ma'am. Thank you.
Okay, so thank you for joining. Yeah, I will.
Thank you so much, ma'am.
Okay, so I will close the session now. Okay, yeah. Okay.